Well, let's start with some recalling on what was done uh, last time. Okay, so we were talking about mass spring systems, and we said that these mechanical systems are actually a mechanical model of other physical phenomena, and then we also discovered that this system is actually modeled by a mathematical object, which is just a matrix. Well, actually, what models the system is the operator associated with this matrix, and then we started talking about what is actually the operator that we should associate with the matrix, and we have this. Well, let us begin with taking a closed symmetric operator, and let us suppose that we have a basis which is in the domain of the operator, and then since the matrix, well, this is not just a sequence, this is an orthonormal basis in the space. We have a fixed Hilbert space, and okay, and since this is an orthonormal basis, the numbers, the complex numbers by these bilineal expressions, then and we take an element in the domain of the operator, then it is true that this thing, which is actually delta J phi, this thing can be written as AJK EK from k equal 1 to infinity, and this phi k is just delta k phi. Okay, so we have the operator acts on the coordinates of the elements of this the coordinates of this element in the domain. Then actually the operator acts as a matrix acting on a vector. Okay, but we already know that if we take an extension of our operator, then we will have that this delta J A tilde delta K is just the same A J K that we had before. And so we define, we gave the following definition. We considered, we say that an orthonormal basis is a basis of representation of the operator A. By definition, this means that there is no a close operator, which is a restriction of our operator A and contains the orthonormal basis. Okay, that was our definition, and let us see what this definition means. Okay, suppose for a moment that we actually have a closed symmetric operator which has these properties, and of course, since this is a restriction of A and these elements are in the domain of B, then delta J B delta K is again equal to AGK. Okay, so we have that there is a smaller operator, smaller than A in this sense, that acts in the same way and generates the same matrix from the vectors from the orthonormal basis delta K delta K. So what this definition is saying us is telling us is that this that we are that we have a basis of representation if there is no smaller operator than A, closed operator than A, which acts in the same way as A on these elements of the orthonormal basis. Okay, so this is what does the definition that we gave at the end of our talk yesterday. Okay, and let us then consider the following situation. Okay, we yesterday wrote the following theorem. We say that if A is closed and symmetric, then there exists a basis of representation. Okay, this is an important theorem. Another important theorem is the following. Suppose that that we have that delta K is a basis of representation of A. Okay. Then the domain of definition of A star is the set of elements in the Hilbert space such that the sum no, sum well, I actually has to put it. this one, from k equal 1 to infinity, from j equal 1 to infinity. Is finite, where of course we are considering that phi k is given by what is by this. Phi k is this one. Okay, so if we have a basis of representation, then we can have an expression for the adjoint of the operator, and of course the adjoint of the operator should also obey this expression. So we can put here a star, and all this is just the same. Okay, so this theorem is actually telling us that if we take a basis of representation, then the adjoint operator is the maximal operator in which the action of the matrix has sense, because these conditions means that the action of the matrix gives us an element which is in the Hilbert space. Yeah, may have to. Okay, so this is our condition, and now let us consider another theorem, which will be important for us. Is the following. Suppose now that we are given a matrix. So suppose that we have a matrix. It's a Hermitian matrix. And suppose that the following condition holds. Okay. Then for any orthonormal basis, there is an operator A which is symmetric and closed, such that this orthonormal basis is its matrix of representation, is its basis of representation, and this matrix is the matrix representation of the operator. I forgot, I think, to say that when we have a basis of representation, then we say that the matrix, probably we'll write here, then the matrix AJK is the matrix representation, of course with respect to this basis of the operator A. Okay. And then this theorem is asserting that if we are given an Hermitian matrix which satisfies this condition, then for any orthonormal basis we have a symmetric operator, a closed symmetric operator, such that this basis, any1, is a basis of representation, and this matrix is the matrix representation of our operator. And actually the construction of the operator is quite straightforward. So if you have this condition, then you can define an operator A naught acting on this vector, which is given by following. And because of this condition, this is well defined. This is an element of the space, and then you extend firstly by linearity, and then you take the closure of the operator A naught, and this closure is by definition the operator A, which clearly is the smallest one, in which we have which contains the basis by construction, just by construction, and then this operator is constructed in this case quite straightforward. Okay, so so we have now the following situation. Okay, let us get back to the matrix. Recall that we have a 3-diagonal matrix, and this matrix satisfies obviously this condition. This condition means that if you sum, this condition means that the columns are L2 sequences, and this is in this case we have just finite sequences because we have only 3 diagonals, and then this matrix, which is clearly Hermitian, satisfies the condition of the theorem, and therefore there exists an operator which I will denote by J. Yeah. Yes, but you are considering the situation point-wise. Yes, yes. So so of course, so we have an operator related uniquely with the matrix, and this is the Jacobi operator. This is the Jacobi operator. Okay, this is the Jacobi operator. Okay, so and also we already know that the adjoint of J is the adjoint of J is given by this expression, the domain of the adjoint of the operator. So this operator is symmetric, and let us now study the kernel of J star minus Zi, where Z is an element, any element in C actually. It is known that for symmetric operator, an important characterization is given by the so-called deficiency numbers. Every time you have a symmetric operator, there are the so-called deficiency numbers, which are just given by the expression J star minus Z. Well, we could put it here I. Think is okay. No, it's not okay. minus plus, the kernel. Sorry, this is the dimension of the kernel of this. Okay, these are the no, it's okay. It's okay because normally you define like the so this is the range, the complement of the range. It's okay. It's okay. It's okay? Yeah, it's okay. Well, so okay, so these numbers, in some sense, give a characterization of symmetric operators, and let us study what happens with the kernel of the operator. Yes, is what Sasha is. But I think it's correct. The definition is the following. Okay, is the dimension of H minus J, the range J minus plus IE. That's this definition. So okay. Okay, so yeah. Okay, so let us look at this expression, and okay. For we already know that this operator is the operator that acts as the matrix in the maximal domain. So let us consider the equation, the difference equation. And let's put Z. And the second one will be, this is B1, this is B1, 5, 1. And in general, Bn minus 1, phi 1 plus Q n phi n plus B n phi n plus 1 equals Z phi. Okay. So consider these equations. This part, the left-hand side is the action of the matrix over the coordinates of phi. So we actually, this equation is of course motivated by this one. This is phi equal lambda phi, z phi. Okay. So this we have this equation, and it's easy to see that this recurrence equation can be solved very easily. You only have to put phi 1 equal 1, and then you know this and this, and you can find phi 2. Actually, phi 2 is equal to Z minus Q1 over B1. Okay? And if you know phi 1 and phi 2, you put this expression in this equation, and you obtain phi 3, which is also a polynomial expression of Z. Okay? So So you will obtain a sequence of polynomials. Let us put way sequence of polynomials where Pn, where the degree of Pn is equal to to n. Yeah? Pn is equal to n. Yeah? So we have a sequence of polynomials given in this way, and of course we have the following situation. Let us denote this sequence by P. Of course, this expression depends on Z. Okay. If and clearly, because this is the adjoint is defined in the maximal domain. If P is an element of L2 sequence, then this element will be a non-zero element in the kernel of in this kernel. Okay, this will be a non-zero element in the kernel because it satisfies the equation. And it is an element of L2. So this is an element of the domain of J star and satisfies the equation. So if this is here, then well, and also it is not difficult to see that any other solution of these recurrence equations is just a multiple of this solution. So it depends only on the value which are given here, because this number defines uniquely the sequence. So if this element is here, then we have that the kernel is a one-dimensional space. So and it is not important because the coefficients are real. It is not important if we are taking a z in the upper, in the lower complex, in the lower half and the upper half of the plane. So in this case, we have that the deficiency numbers are just equal 1. If it happens that this sequence is not in L2, then obviously there is no solution of there is no element except the trivial one, the 0, in the kernel, and then the deficiency indices are just 0. And these are the only two cases for Jacobi operators. So Jacobi operators have either 0, 0 or 1, 1 deficiency indices. Okay, and it is known that if an operator, symmetric operator, has deficiency number 0, 0, then the operator is self-adjoint. The case when this happens, and in the other case, we have just a symmetric operator which is not self-adjoint. Yeah. 5 diagonals. Yes. you no no. If you have, for example, 5 diagonals, you will have either 0, 0. You could also have 1, 0, 1, 2, 2, 1, 2, 2. If it is, it could be symmetric and have different efficiency indices. Yeah. But I think that let me see. In this case, the deficiency numbers are equal. I think. Yes. Yeah. 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 Okay. Yes. Yes. Okay. Well. Okay. Another important thing that can be obtained from this recurrence equation is the following. Actually, since the matrix is symmetric, it is also true that J delta K, delta 1 is equal to Q delta 1 plus B1 delta 2, and in general J delta N is equal to this Q to Bn minus 1 delta N minus 1 to N delta N plus Bn delta N plus 1. This can be verified straightforwardly, and if we try to express, for example, this element of the basis in terms of the other elements, we arrived at the following situation. We have that these same polynomials evaluated in the at the operator and acting, for example, here, this gives us this one does. Yeah, this can be shown directly. For example, delta 2 is given by the 0 polynomial, which is just 1. Yes, acting on, is this correct? Oh no, I think this is n. Yeah, because the 0 polynomial is not playing. Okay, so this is correct. Yeah. Yeah. For example, this is the polynomial with the subscript 0. This is the polynomial 1, and yeah, we have written this way, n minus 1. This is the polynomial of degree 0. Yeah. Yeah. Okay, so but still there is a problem here, yeah? Because we have that delta 2 is equal to the first polynomial, so it was fine. Delta 2 is equal to the first polynomial acting to this one. Yes. Okay. Okay, so now this is correct. Okay, this is correct. Good. Okay, so we have this situation. Okay, Okay, and this simple expression has various consequences. The first one is that delta 1 is in the domain of all the all the powers, all the powers of J. Yeah. And the second, this is the first consequence, and the second, which is related with this one, is that J, that if J is self-adjoint, that is when we have 0, 0 deficiency indices, then J is simple. Well, I will maybe skip the explanation of why this is so. Actually, it is quite straightforward, but we have to know what simple operator means. But in this case, it is sufficient to understand that this implies, in the case when this is an operator with only with eigenvalues, this simplicity means that these eigenvalues have multiplicity 1. Okay. In the general case, simplicity is something more complicated, but for now, this is sufficient for us. Okay. Okay, so let me see. Okay, so we have this situation, and let us now skip to other thing. Okay, so we have now some understanding of what a Jacobi operator is. Probably I should say some more words about this situation. So the spectrum is simple, but also we have that if we have there is a theorem says that if you have a self-adjoint operator and this operator is simple, then there exists a basis an orthonormal basis which is actually a basis of representation for this symmetric operator, such that the matrix representation of A is a Jacobi matrix. Okay. So every self-adjoint operator, every simple self-adjoint operator is actually a Jacobi matrix. It's a Jacobi operator. And we know that, for example, in physics, people are interested in self-adjoint operators. Self-adjoint operators, not all operators are simple, but all can be decomposed simple operators. So all operators, in particular all the self-adjoint operators relevant to quantum mechanics, are actually orthogonal sum of Jacobi operators. Also self-adjoint, yes. In particular, those relevant in quantum mechanics. Yeah. Okay. Okay. So now we will forget for a moment about Jacobi operators. And consider the following problem, the moment problem. Well, I just remind you that I warned in the first lecture that our model is related with many branches of analysis. And we will now ask the following question. Suppose that we are given a sequence of real numbers. Okay, and I want to ask the following question. When this sequence of numbers, let us enumerate them from 0. When this sequence of numbers are given by expressions of this kind, where this is a Borelian measure. Okay, when can we find a measure such that our sequence is given by this expression? Okay, this is the so-called moment problem. It is a problem which was very important when the mathematical analysis was in its beginnings, and well, now you can certainly say that the problem is solved in the sense that we know when we can expect to find a measure. We also know how to find these measures. But okay, so the first part of the question is, when does a measure exist such that this happens? This is the first part of the question, and it happens that if you take this sequence of numbers and arrange them as follows. In a matrix, and then take the determinant of this, and it happens that this determinant is greater than 0 for any m in n. Well, and well, I will write this, meaning that S naught is greater than 0. Okay. If you have a sequence that satisfies this condition, then there is always a solution of the moment problem. And the converse is also true. If there is a solution of the moment problem, then the sequence of moments satisfies this condition. So let us denote by n all sequences that satisfy this condition, and let us call these moment sequences. They are called moment sequences because they are actually moments of a certain measure. Okay. Okay. So now something interesting happens. I will use the spectral theorem, which you already have heard of it in the preceding lecture by Ricardo Vedder, Actually, the spectral theorem tells us that if you have a self-adjoint operator, then the operator can be expressed just by a simple integral, where this thing is called a spectral measure, and is something like a measure, but it takes values in the set of projectors in the Hilbert space. Okay, so let us assume that that we have this spectral decomposition. This measure also have the property that if you take the quadratic form of it, for example, from delta 1, let's suppose that this is a Borel set. If you take this quadratic form, then this is just a normal measure, a measure which is known for you, evaluated in this Borel set. Okay, and let's see what happens. Of course, if you have a function, actually the set of functions that you can put here is quite wide. Then a function of the operator can be defined in this way, and this is what we want to do now. So, for example, if we take this expression, and use the spectral theorem of delta 1 a delta 1, okay, and there is a result. Well, I will put here a exclamation mark, and this can be written as the integral of tk d mu delta 1, just as we had here. Okay, but look what have we found. This sequence is a sequence of moments because of this. Okay, so we have easily constructed a sequence of moments. But for this to be true, one has delta 1 to be in the domain of all these operators. We know that this happens if we take our Jacobi operator here and assume that J is self-adjoint for the moment. So Jacobi operators in a very straightforward way defines sequence of moments. Okay, and the thing is even more surprising, because if you are given, for example, a Jacobi operator which is not self-adjoint, then since the efficiency indices are 1, 1, this was already established, then we know this is a result of the so-called extension theory for symmetric operators. We know that there are a family of self-adjoint extensions of our operator, our symmetric operator. And if we take obviously delta 1 is in the domain of jk for every k, and this assertion is independent on the fact that j is self-adjoint or not. But if we take so this expression always has sense independently on the value of the deficiency indices. Okay. But if j is self-adjoint, we already know that this thing is a sequence of moments. If it is not self-adjoint, we can put here an extension. Yes, okay. An extension of this, and obviously this is equal to delta 1 j k delta 1, and this is true for every extension, which now we are parameterizing by beta. Okay. So okay, so we have that. If our starting point is a Jacobi operator, we can generate. Well, if it is yeah, it is not important if the Jacobi operator is self-adjoint or not. We can generate a sequence of moments, and on the assertion in the opposite direction is also true. If we begin from a sequence of moments, then we can this means that we have this situation, and if we consider the space L2 mu, then it is easy to see, because of this condition, that this sequence is in this space. Okay, then I can apply the orthonormalization process of Gram-Schmidt to this sequence, and we obtain a sequence of polynomials and here the magic comes. It turns out that these polynomials satisfy a recurrence relation of this kind. Q1 P, well, I have to put P naught because we began at naught, at 0, plus Q plus B1 P1 is equal to Z P naught. And well, I will not write the next equations, but we can generate a Jacobi operator from sequence of moments. Well, if we know the measure, of course. Okay, by orthonormalizing this sequence. Okay, so every sequence of moments also generates a Jacobi operator. So there is a one-to-one correspondence between the set M and the set, let us denote them by J, the set of all Jacobi operators. But this is actually even, there is more magic in all this, because yeah, 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 No, because I am when you have a non-self-adjoint Jacobi operator. I'm referring to the Jacobi operators, not to their self-adjoint extensions. Okay. So if the operator is not self-adjoint, you have a lot of self-adjoint extensions, but the Jacobi operator is the symmetric one. Okay. But here is an important point. If M is okay, if you have a sequence of moments, you can ask if the solution is unique or is not unique. Okay. If the solution is unique, the problem is called determinate. If it is not unique, it's called indeterminate. So the set M is partitioned into the set of indeterminate and determinate moment sequences. Okay, and here it can also be. We have already shown that if J is not self-adjoint, if the Jacobi operator is not self-adjoint, then we can generate more than one solution for a moment problem. Actually, all self-adjoint extensions of the operator generate a solution of the moment problem. Okay, so and it can be proven. Will not do this, that there is a one-to-one correspondence also here between indeterminate sequences and self-adjoint Jacobi operators with deficiency indices 1, 1 and determinate moment sequences with self-adjoint Jacobi operators. That is, Jacobi operators with indices 0, 0. Okay? So there is a lot of magic here, I think. This is quite relevant that things happens in this way. Okay, so okay, so let us now so how I am in time? Anyone knows? Huh? If you want to have a break, or yes, okay. Let's do a 5 minutes break. Okay. Okay, so let's continue. So now we know that you know a little about the Jacobi operators, and we want to construct now some functions that are important for us in order to carry out the direct spectral analysis and the inverse spectral analysis. First, well, we already know that a Jacobi operator is if the operator is self-adjoint. The operator is self-adjoint. Well, let us now use the following notation. Let us assume now that J, probably I want, not a good idea to use the same letter, but well, let us use A. Yeah. Let now A be the be either J when it is self-adjoint, or an extension of J when it is not self-adjoint. A self-adjoint extension, self-adjoint extension of J when probably this is not the best. Not self-adjoint. Okay, so this is our operator A. So A is always self-adjoint. And as I have already said, every self-adjoint operator is actually orthogonal sum of these kind of operators. For example, if you have the Schrödinger regular operator, then as it is known, this operator is simple, so this is just a Jacob operator. And what about the spectrum of A? What about the spectrum of A? Well, since it is self-adjoint, this spectrum is not empty. And since this can be actually every simple self-adjoint operator is a Jacob operator, then this is every subset of the real line, any subset of the real line, is actually the spectrum of a Jacob operator. So that is, if you give any, this is a Borel set of the real line, any Borel set of the real line, or any Borel set of the real line, there exists a Jacob operator, actually self-adjoint, because I will talk a little about this situation. There exists a self-adjoint Jacob operator such that the spectrum of J is this set. Okay. This means that if we consider delta 1 J, in this situation, J is self-adjoint, delta 1 is actually any measure. This means the support of this measure is any Borel set, the real line, and for any measure we can find an operator. Of course, we have that because this is a spectral measure, and this thing is actually this thing. This is the identity operator. Because this thing is this thing. That means we have that measures that are spectral measures of Jacobi operators. Of course, are any measure, but they satisfy. They are normalized in this sense. They are normalized. All measures are finite measures. But we have actually the following assertion that I put the following assertion. Well, of course, yeah. It's normalizing that. It's normalized. Yeah, because you can always, yes, you're right. Here you're right. You have to normalize the sequence of moments, yes. And we had just this condition, but you can always consider just that S naught is equal to 1. What I'm doing. Yeah, so you can just consider that our set M is the set where the moments have been normalized in this way. Okay, so we have the following a measure. Let us write this way. A measure, a Borel measure, is the measure of a Jacobi operator if and only if well, we have to put if and only if if and if if and only if well, first this happens. A measure, let us put here mu, happens, and all the moments okay, so and actually this is not true. Statement is not true, but it will be true within a moment. Okay, this is what we have established. We have established that if you have a measure, if you have a Jacobi operator, that its spectral measure satisfies these two conditions. This has been already established. But well, the fact that we can go in the opposite direction has already been mentioned before, when we say that we can construct a Jacobi operator from a sequence of moments. But I left an important detail unaccounted, and this is the following. suppose that all moments exist. Then you have this sequence in this space, and you can orthonormalize these sequences. There is no problem. But what if this is not dense in L2? What happen, actually? If this is not dense, then after orthonormalizing, you won't get a basis. Of course, we can solve this problem, and this is the third point that the polynomials are dense in L2 are mu. Okay, so this is the necessary and sufficient conditions that a measure should satisfy in order that it is a spectral measure of a Jacob operator. This is the necessary and sufficient condition. Okay, and now let us consider, suppose that we have this spectral measure. Yeah. Yeah. Because yeah. Yeah. Yes, this is actually not a trivial question. Not a trivial question. Huh? No, it's not a trivial question, and it was established by Ahieser that if you take probably, I don't know, probably, yeah, but yeah, but actually in the theory of the moment problem, the question is solved differently. The what is classically done, for example, in the book, I recommend the book by Ahieser. There is a book, which is a classical book. It's the classical moment problem. It has a subtitle, but nobody cares about the subtitle. So this is a classic book. I think that it is beautifully written, my opinion about this book. And well, in for example, the way Ahieser addressed the question by Sasha was that yeah, I know that, yeah. Yeah, maybe. Okay, well, but nevertheless, I recommend the reading of this book, and yes, it is the book. It's for the 50s, yes. It's for the 50s. Yeah. Well, but okay. But it is established some way that if you part from a Jacob operator, well, I think it is not difficult to establish. Yeah, that you can do even with the. Okay. Okay, but okay. But we have this necessary sufficient condition for a measure. Okay, so we have a complete characterization of the measures that are related with Jacob operators, and now let us take the Borel transform. I call it Borel transform, but again, probably it is not called in this way. If we take the Borel transform of the measure, we have a function which is called in this setting the m-bile function. This is the m-bile function. Sorry? I don't know what is the correct form. Yes, you're right. Okay, violent function. Okay, violent function. Who's vile? I'm not the only one that write this way. Okay, the violent function. And this, of course, is if we use the spectral theorem. This is just delta 1 times. Let us use our notation here. A minus z minus 1 delta 1. This is the violent functions, that is the action of the resolvent or the quadratic form of the resolvent with respect to delta 1. Okay, so since we have a complete characterization of the measure, actually we have a complete characterization of the violent function. And it is known that there is a one-to-one correspondence between measures and their Borel transform. So there is a one-to-one correspondence between the spectral measure and the violent function. Okay. Okay, and let us also introduce another function which will be useful for us. The green function. The green function. Which is defined as follows. This is just the resolvent acting on the n vector. This is the green function. Of course, we'll have expression in terms of the spectral measure. Okay, and there is a lot of expressions that are related to the green function. Okay. es el mismo. Huh? Side the integral, yes, this is the same as this one. Ah, sorry. Yes? The green. Yeah, this is a problem of mine. Okay. Okay. Yeah. Well. Okay, so at this point we return to our setting, our original setting. We have this system of masses and springs, and we perform a perturbation in one mass and in one string at some point. Let's suppose that this is at the point n. So this is the first spring constant, this is the first mass, and we change the n spring constant and the end mass. Okay. Let's write our Jacobi matrix. This way, and our perturbation corresponds to changing the following. We have b, instead of bn, have theta bn minus 1. We have here theta bn minus 1, the square un plus h, theta bn bn, and all the other probably I will and the rest are just the same. So we have just changed these entries of the matrix when we perform this kind of perturbation. Let us say what is so the increment in the mass is equal to mass, the nth mass, times theta minus 2 minus 1, and the increment in the spring constant is equal to minus okay, and if we have this, of course, these entries are completely determined by the spring constants and masses of the system. Okay, and what happens here? Okay, let us consider the following. If you see, we can just following, and here we have a finite Jacobi matrix. This is a finite Jacobi matrix. And here we have an infinite, or semi-infinite Jacobi matrix. Okay, and as any Jacobi matrix, we can consider the let us call this one J minus n. This is this Jacobi operator, and this Jacobi operator will be J n plus. Okay, and we will also consider the Weil function of Jn, Weil function of Jn minus, and we will denote this by this, and the Weil function of J plus this way. Okay. Okay, and then we have the following result, which I whose proof will be skipped. Actually, we haven't proved anything. It's a problem, but prove some results in our last lecture. Okay, so it turns out that the green function can be given by the following expression: E squared m n plus z minus 1 squared m z plus z minus okay okay okay, we have this expression, and this expression is actually interesting because it turns out that if we know the Weil functions of these two matrices, then we know the green function of the whole matrix. Of course, we also need to know these constants, okay, which are the constants that are here in this. Of course, if you take the perturbation, then your green function changes, and now you have, instead of bn squared, you have to put theta squared b n squared am n plus z plus theta squared b plus z plus theta squared q n plus h. What? Minus, yeah. Okay, so we have this expression for the perturbed system and this expression for the original system, and as you see, these are just the same functions, so this will be very useful for us. Particular, we have the following interesting thing. We will introduce another function. I denote this way. Okay, this Z is Z. Okay. Would be just the original green function. And this will be the perturbed green function. And here we have to do some assumptions in order that this has sense. Okay, so we already know that we actually have any kind of a spectrum. But let us assume that the spectrum of A is the Jacobi operator or a self-adjoint extension of it. Is discrete. That means that the essential spectrum is empty. Well, probably some of you does not know do not know what essential spectrum, what the essential spectrum is, but this condition means that the spectrum of the operator is a sequence with no accumulation points on the real line. Okay, this condition means that we have a sequence of points with no accumulation points on the real line. So let us assume this. If we assume this, well, I have already, then it is clear that the Weyl function of the operator is a meromorphic function. A meromorphic function. The poles of this function are just the eigenvalues of our operator. Okay. Okay, so we have a meromorphic function, and of course, if we are assuming that the essential spectrum of the matrix is empty, then the same is true for this matrix and this matrix. Well, this matrix is always the case because it's a finite matrix, but the assumption on the absence of the essential spectrum of the whole matrix implies the absence of the essential spectrum of this submatrix, and then therefore, if we have this function, this meromorphic function, then m, n plus and minus are also meromorphic functions. Okay. Okay, this would be essential because then we know that the green function is a meromorphic function, and this is also a meromorphic function, and this quotient is also a meromorphic function. And there's also say that if you take the Borel transform of a measure, was what we did, it is also a basic result in the theory of functions that this function is a so-called Herglotz function. This is a consequence of the so-called Nevanlina representation theory. Okay, so this is a Herglotz function. This means, in particular, that but if Z is in C plus, then MZ is in C. Okay. Okay, so well, I think I have done the preparations for solving the direct and inverse spectral problem that will be done in the next lecture. So probably I will stop here. Yeah. The same, the same, the same. This. Well, but this is a consequence of the definition. Okay, if you have yes, the green function actually is a matrix. It's a matrix. So when you put the resolvent A minus Z minus 1 and you put here delta 1, this is just the Weyl function. If you put here JK, this is the green function actually, the green matrix, or the matrix of the green function. Yeah. So this is the analog of what is the green function in differential equations. Yeah. Huh? Because if you have this, you have the resolvent. The resolvent is what you need for solving your problems. Yeah. And now you, instead of seeing an integral operator, you have to put this in a double in a sum, and this is just the same situation. Yeah, yes. I'm taking a part of the green function. Yes. It's a part of the green function. Yes, but this is called the green function. Yeah. Yes. Okay, it's just the diagonal. Yeah, because I'm not interested in the other elements. Yeah. Okay. It's called the green function by me. Okay. Yeah. Well, it will solve our problem. Yeah. Okay. Well, thank you. Let's we see tomorrow. No, on Monday. No, there are no more questions? No questions? No? Okay. Thank you.